So once we've found our critical points, those become our candidates for the local extrema. But we need to test them. They could be any given critical point could be a maximum or a minimum, or it could be neither. And in order to test them, we have to look at points on either side. And that brings us to our one of our first major takeaways from this section, and that's the first derivative test for local minima and maxima. So what we're going to do is just start with our critical points, right? We start with the critical points, and then we look at either side of the critical points, and we look at the slope, right? Essentially, we're going to look at the first derivative, which is the slope on either side of the critical point. And if the slope changes from negative to positive, so here's an example, it's changing from negative to positive, right? Then we have a local minimum, all right? So here's our local minimum. Well, local minimum, it says right here, doesn't it? Local minimum, all right? If it changes from positive to negative, so if we look at this case, the slope on the left side is positive, and then it becomes negative, and then the critical point is a local maximum, okay, local maximum. So let's apply the first derivative test in example 3. Now we're going to use the same function as example 2. And if you recall, that function was f of x equals x cubed minus 9x squared minus 48x and plus 52. Okay, and we found that the derivative was, after we factored it, it might be easier in factored form, we found the derivative was 3 times x minus 8 times x plus 2. I'm just going to write it in factored form in this case. And in order to evaluate the critical points, which we found to be, I'll just write critical points. Okay, we found those to be x equals negative 2 and 8. Okay, so we need to test them now. We just need to test them to find out whether they're whether they're local minima or maxima, or perhaps neither. All right, so we need to evaluate the derivative on either side of these points. So what I'm going to do, I'm just going to draw a little number line. Okay, this is just where I'm going to kind of record my information that I'm finding out. So we need to test the intervals around negative 2 and 8. Okay, so I need to pick a point somewhere on either side of these other points. So if I want to test the point negative 2, x equals negative 2, I'm going to test a point on either side. All right, so I'm going to test a point. Let's say I test negative 3, and I'm just going to look at what is the derivative at negative 3. That's just a point to the left of negative 2. So if I plug that into my derivative function, whoops, I forgot my prime there. That's f prime. That's the derivative. All right, I'm just going to plug that negative 3 in there, and what I get is I get 3, and then times negative 3 minus 8, so that becomes negative 11, and then this last factor becomes negative 3 plus 2, which is negative 1. So I get a positive 33 when I multiply that out, right? Because a negative times a negative is a positive. That's greater than 0. Okay, so that's telling us that f is the original function. F is increasing in that interval that's less than negative 2. Okay, as long as it's a continuous function. All right. So we can test a point to the right of negative 2. So probably an easy one to test would be 0. So I'm just going to plug in 0 into the equation I have for the derivative. All right, so I'm going to take 3 times 0 minus 8 is negative 8, and then 0 plus 2 is 2, and when I calculate that out, I get a negative 48. Now that is obviously less than 0, so this is telling me that f is decreasing. All right, so I can actually record both of those with little arrows. So increasing, so we know it's increasing from, to the left of negative 2. So I'm going to draw a little arrow going in the up direction. Okay. And then it's decreasing. It's decreasing to the right of -2. So I'm going to draw a little down arrow. It's decreasing. The function is decreasing. All right. So what's that telling me? That's telling me that -2, as long as it's continuous at -2, which it is, I'm going to have a local maximum. All right. So I have a local maximum at -2. But let's go ahead and test the other point too. Let's test the point to the to the right of 8. So I'm just going to pick something like 10. 10 is to the right of 8. So I'm just going to put 10 into the derivative function that I have. So 10 minus 8 is 2. 10 plus 2 is 12. And so I get 72. And that's greater than 0. That's all I really care about is the sign of it, whether it's positive or negative. So because it's positive, this is telling me that f is increasing again. F is increasing to the right of 8. So I'm going to draw a little arrow. So that just helps me kind of visualize what's happening. That the function, so you can imagine the function is doing something like this. It's going down and up and down. And you can see, well, I didn't quite line it up, but at -2, I'm going to have a maximum. And at 8, I'm going to have a minimum, right? Because I'm going from decreasing to increasing. All right, so let's summarize the result here. So we can say that f of x has a local maximum at we calculated the values of these functions in example 2. So I'm going to say the maximum of the function is 104. Okay, that was the value of the function. And the x coordinate is x equals -2. So we can say that it has a local maximum of 104 at x equals 2. Oops, -2. -2. And we can say that f of x has a local minimum of this is supposed to be of I wrote at I meant to say of here of all right of so the minimum is a -396, which I calculated in example 2 at x equals 8. Okay, so that's my local maximum and minimum for this function. All right, so I will meet you in the next video.